Beneath inland Queensland, in a stretch of ground that has been mapped, drilled, and studied for decades, geologists have started to suspect they missed something. Not a new basin, not unexplored territory. These rocks have been known for years, tied into the vast Bowen and Surat Basin system that underpins much of eastern Australia's energy. The maps exist, the wells exist, the hydrocarbons were never a secret. And yet attention has snapped back to a deeper, stranger part of that system, a place called the Taroom Trough, with a suggestion that sounds almost impossible, that it could become Australia's first new oil province in more than half a century, which doesn't make sense at first. If the rocks were always there, if the basin was studied, if the oil was already known, how do you discover an oil field in a place that was never really hidden? The answer is that the oil isn't new. The understanding is. Here's the thing that's easy to miss. The scale of this was hiding in plain sight. The Taroom Trough is not some small, isolated pocket. It's a deep furrow in the crust, roughly 43,000 square kilometers of it, buried inside a much larger machine, connected to the Bowen Basin to the north and the Surat Basin to the south. Together, they form one of the most extensive sedimentary packages on the continent, stretching across hundreds of kilometers and preserving a record that reaches back more than 250 million years. So the question was never really, is there oil here? That's been answered. The question is far harder and far more interesting. Where is the oil that's still left? And has anyone actually drilled into it yet? To understand why that question is so hard, you have to go back to a time when this landscape looked nothing like Queensland at all. During the Permian period, this entire region was low, wet, and green, not desert. The opposite of desert. Dense vegetation. Thick forests spreading across broad floodplains and wetlands. Plants lived, died, and were buried over and over for a very long time, piling up thick accumulations of organic material that would eventually compact into the rock we now call the Blackwater group. At the time, it was just plant matter, dead swamp, layer on layer. But bury plant matter deep enough, give it enough heat and enough pressure, and it stops being plant matter. It becomes something else entirely. The basin didn't stay still. Through the Triassic and into the Jurassic, it kept subsiding, and more sediment poured in. Sandstones, mudstones, whole sequences stacking up kilometer on kilometer. Among them were the units that would matter most: the Snake Creek mudstone, rich in organic content, and the Precipice Sandstone, a porous rock that would one day become critical for holding oil. By this stage, every ingredient for an oil system had been assembled, but nothing had actually happened yet. That came later. As burial continued, the temperature climbed. Slowly at first, then sharply, as the deepest parts of the trough were pushed further into the earth. Tens of millions of years after the source rock formed, the deepest layers finally got hot enough to trigger a transformation. The organic material locked inside those old Permian coal measures began to break down and release hydrocarbons. This is the moment the whole system switches on. The Blackwater group didn't just sit there. It started generating oil, and in large volumes. And not only oil, gas as well, depending on exactly how hot each part of the basin became. In some areas, the conditions were perfect for liquid oil. In others, temperatures pushed straight past that window and cracked the oil into gas. But generation is only step one. What happens next matters just as much, because oil does not stay where it forms. Once it's generated, oil starts to move. Driven by pressure and buoyancy, it migrates upward through the rock, escaping the dense source layers and slipping into more porous pathways. In the Taroom Trough, sandstones like the Precipice became exactly those pathways. Underground conduits that let oil travel sideways for kilometers. The oil is no longer tied to where it was born. It's moving, searching for somewhere to gather. and that has a consequence people find counterintuitive. The location of an oil field has very little to do with where the oil actually formed. It all comes down to traps. Long before any of this oil existed, the basin had already been bent out of shape. During the Triassic, compressional forces folded and faulted the rock, creating subtle structures, anticlines, pinch-outs, stratigraphic traps. At the time, they were just quirks with no particular meaning. Tens of millions of years later, they became everything. When the migrating oil ran into one of these structures, it couldn't keep going. It pooled beneath an impermeable layer and built up, over time, into a concentrated reservoir. Fields tied to the Precipice Sandstone didn't form because the oil originated there. They formed because the oil was caught there. And here the system shows how tangled it really is. Geochemical studies find not one type of oil down there, but two distinct families. The dominant one is sourced from the Permian Blackwater group, feeding reservoirs across a wide range of formations, the Precipice Sandstone among them. Geologists call it the Blackwater Precipice System, and it's the main engine of the basin, the source of most of the hydrocarbons anyone has identified. Running alongside it is a second, smaller system, sourced from the Middle Triassic Snake Creek mudstone and reservoired in the showground sandstone. Less significant in total volume, but still fully capable of generating and trapping oil under the right conditions. At two fields in particular, Roswin North and Red Nook, this secondary system becomes locally important, building its own separate accumulations. So the basin isn't a single clean system. It's layered, overlapping, interconnected. And that's exactly where things start to fall apart, because not all of that oil is still there. In the northern parts of the trough, burial went too far. Temperatures climbed past the ideal range and pushed the system into overmaturity. Oil that had already formed cracked into gas, and in some cases escaped entirely, leaking up through faults and bleeding out to the surface across geological time. The system worked, it just didn't stay intact. What's left across much of the north today is mostly dry gas, which paints a misleading picture, because if you look only at modern production, the basin can appear gas-dominated, even though it originally generated enormous volumes of oil. The real story is further south. There, conditions were kinder. The rocks were buried deep enough to generate oil, but not so deep that it was destroyed. Migration pathways were active, and crucially, the traps were already in place at the right moment. That timing is the whole game. If a trap forms too early, the oil can bypass it. If it forms too late, the oil may already be gone. But in the south, the sequence lined up almost perfectly. Oil generated, migrated, and caught in traps ready and waiting to hold it. And not all of those traps have been drilled. None of this is theoretical. This exact system has already produced a major oil field once. In 1961, drillers on the eastern flank of the trough hit oil where the Precipice Sandstone had draped over an older Bowen Basin high, a textbook structural trap filled with crude that had migrated up from Permian source rocks below. They called it Moonie. 3 years later, in 1964, it became the first oil field in Australia to flow commercially, and it remains the largest single oil accumulation ever found in the Surat Basin. Moonie proved every link in the chain: Permian source rock, working migration pathways, a trap that formed at the right time and held. Everything the geochemistry now describes, Moonie demonstrated in the field 60 years ago, which is why the current excitement isn't really about whether the system works. It's about whether the same machine that made Moonie built other traps nearby that nobody has drilled yet. That's the part that keeps geologists awake. The migration pathways were extensive, the trapping mechanisms were widespread, and the basin is large enough that it's genuinely unlikely every viable structure has already been tested. This is not a frontier in the sense of being unknown. It's a frontier in the sense of being incomplete. Modern exploration here isn't trying to prove oil exists. That question is closed. It's trying to find the accumulations still down there, and it's chasing them in two very different ways. The first is the classic hunt, the pockets generated millions of years ago that never escaped, sealed in traps that were filled and never breached. That's a question of precision, finding reservoirs that held their porosity and pathways that led oil into exactly the right place. The second is deeper and much more modern. Some of the biggest prizes here aren't in neat conventional traps at all. They're locked in tight, overpressured rock 3 to 4 kilometers down. Oil and gas held in stone too dense to flow on its own. The same kind of unconventional play that transformed the American shale basins. Reaching it means horizontal wells and hydraulic fracturing at extreme depth, not a simple hole into a pool of crude. And the first barrels are already moving. One operator's pilot is producing around 200 barrels a day of light crude. Nothing against a country that burns more than 1 million a day, but proof this rock can give up oil right now, not just in theory. But there's a reason to stay skeptical. And it isn't about whether the oil is there. It's about what kind of oil it is. The crude coming out of the Taroom Trough is light. Light crude refines into more petrol than diesel. And Australia's real vulnerability isn't petrol. It's diesel, the fuel that runs the mines, the freight, and the farms. More than half the oil the country consumes is diesel, so a basin full of light crude does comparatively little to fix the actual shortage. Then there's the depth and the fracking. The richest targets sit kilometers down and would need extensive fracture stimulation to produce at scale. Expensive, slow, and certain to draw opposition. The whole thing is still at the appraisal stage. No one is producing at commercial volume yet. So when a state government calls it Australia's first major oil province since the 1970s, that's a real possibility. But it's a hope backed by early wells, not a proven bank of barrels. The geology is genuine. The scale is not yet confirmed. So, are there new oil fields waiting under Queensland? The honest answer isn't a clean yes or no. The system is there. The oil was generated, it migrated, the traps formed, and Moonie already proved the whole sequence can work. The only open question is whether the right structures are still down there undrilled, and whether the oil inside them is worth the depth and the cost of reaching it. In a basin this large, with a history this tangled, it's entirely possible some of them are, unchanged since the moment they filled, hidden beneath a flat, unremarkable landscape that gives no hint of what lies below, quietly waiting for someone to drill into exactly the right piece of rock. If you enjoyed watching this video, don't forget to like and subscribe. Let me know in the comments which topic should be next.